Hey there everyone, today we're going to be finishing up our unit on triangle applications, and we're going to be looking at finding the area of a triangle. Okay, let's start with a little warm-up here. Here I've got a few convex polygons on the screen, and what we'd like to do is try to divide each of them into a collection of triangles. You can only do so by connecting two vertices together with a line, and those line segments, they cannot intersect one another. Okay. Now, once we do this for each of the figures here, we're going to try and come up with a relationship between the number of sides that the polygon has and the number of triangles that it can be divided into. Okay. So let's start with the pentagon there. Now, keep in mind there are multiple ways that I can divide this up. I'm just going to give you one example for each. So for the pentagon, how about we connect these two vertices? And then how about these two? That's going to be it. If you try to connect any other two vertices together, your line segments are going to intersect one another. For example, if I did that, notice we're intersecting. Okay, so see, we're ending up with 3 triangles here. For the rectangle, you're going to get 2 triangles. And then for the arrow, lots of different possibilities here. Let's go with this. Notice I'm ending up with 5 triangles. Okay, so now consider the number of sides in relationship to the number of triangles we've divided these figures into. So for the pentagon, you've got 5 sides and 3 triangles. For the rectangle, 4 sides and 2 triangles. For the arrow, we have 7 sides and 5 triangles. You see the connection there? The number of triangles is equal to the number of sides subtracted by 2. Okay. Now, really, what I'm getting at with this warm-up is that if I can find the area of a triangle, then I should be able to find the area of any polygon, any convex polygon, because of the fact that it can always be divided into a collection of triangles. Okay, so let's segue into area of a triangle. You've worked with this formula for years. We know in general area is equal to 1/2 times the base of the triangle times the height of the triangle. Okay, now let's dig a little deeper into this. Understand that the height of the triangle is going to be equivalent to the length of the altitude of the triangle. In this picture, this dashed line represents the altitude. Okay, and it's simply the line that you create by connecting a perpendicular line segment to the base of the triangle with the opposite vertex or opposite angle of the triangle. Okay, so again, can't stress enough, the base of the triangle has to be perpendicular to this altitude, and the length of that altitude is the height of the triangle. Okay, all right, move to example 1 here. Notice I have a oblique triangle here where I'm given 2 sides and an included angle. So this is a side angle side situation, and I'm asked to find the area of the triangle. Common mistake, sometimes students just take 1/2 multiplied by 2 multiplied by 5 here, where they think of 2 and 5 as the base and the height. Understand that neither one of those measurements represent the length of an altitude for this triangle. Okay, so I'm going to draw my altitude from the top vertex down to the bottom side length. So there is the height of the triangle. Okay, so the first thing I'm going to have to do is come up with a value for h here, and I can just use some right triangle trigonometry on that right triangle that's got the 46-degree angle associated with it. So I can take sine of that 46-degree angle It's equal to the opposite side length, which is h, divided by the length of the hypotenuse, which would be your 2 units here. That means h is equal to 2 times the sine of 46 degrees. Now I'm able to find the area of the entire triangle. The area will equal 1/2 times the base of the triangle, and based on how I drew in my altitude, the base has to be 5 units, the side that's perpendicular to that altitude, multiplied by h, which is this 2 times the sine of 46 degrees. Okay, so let's punch that in, and we end up with 3.60 square units. Okay. All right, now notice that final area was equivalent to the product of our 2 triangle side lengths that were given multiplied by the sine of that included angle. Okay, so knowing that, we can adjust our area formula slightly. Notice in this picture, I'm given side lengths A and B and their included angle C. So based on what we just saw, the area of this triangle can now be thought of as 1/2 times the base, which in this case is B, times the height, which would be A multiplied by the sine of angle C. All right, now if we dropped altitudes from either of the other 2 vertices in this triangle, then that means the area could be thought of as 1/2 times A times C multiplied by sine of their included angle, which would be angle B. Or you could have 1/2 times, let's do C times B times the sine of angle A. Okay. Moving on to example 2, let's apply the formula, the newly adjusted formula here. This is another side angle side situation. Area can be thought of as 1/2 times 2 times 5 times sine of the included angle. Okay. So we're ended up with 4.98 square units for the area of this triangle. All right. Now if you move to example 3, notice the situation's a little different. This time the givens are the 3 side lengths. So this is a side, side, side situation. And we are going to need an additional calculation to come up with the height before we can come up with the height of this particular triangle. So I'm going to choose to drop my altitude from the top down to this side length of 9 units. And how about I go after this angle X here? Okay, I can find that value with the law of cosines, So the opposite side length to that angle X is 8. I'm going to square that and equal it to the other 2 side lengths squared and added together, subtracted by 2 times their product times cosine of that angle I'm trying to find. So simplify here a little bit. Subtract the 81 and the 25 over, you'll end up with a negative 42 equals negative 90 times the cosine of angle X, and X would equal inverse cosine of 42 over 90, which is 62.18 degrees. Once we have that, we can apply our new area formula in terms of sine here. So area is going to equal 1/2 times, I'm going to have to do the two included, or the two side lengths that that angle is included in between. So that would be 5 and 9, then multiplied by sine of that included angle. Okay, so 1/2 times 5 times 9 times the sine of the previous value, 62.18, should give us around 19.90 square units. Okay. All right, last example. This time I'm working with a parallelogram. And this is kind of where the warm-up kind of comes into play here. I can divide this parallelogram into two triangles just by connecting, let's say, these two vertices here. And the nice thing about this being a parallelogram is I know that these two side lengths are congruent. So this is 4.6 feet. And then these two side lengths are congruent to where this is 1.3 feet. And that means the two triangles here are both going to have the same area. So if I can come up with the area of one of those triangles, all I have to do is double it to give me the area of the entire parallelogram. Notice for either triangle, we've got a side angle side scenario here. So my area is going to be nothing more than double the product of 1/2, 4.6, 1.3, and the sine of their included angle, which is 78 degrees. Okay. Multiply that all out. And I'm ending up with approximately 5.85 square units. Or actually, we know the units here. These are feet. So square feet.